there are two types of improper integrals. We're going to start talking about type 1. And what this is this contains a negative infinity or an infinity as a limit of integration. These are a little bit easier to diagnose because you can see the infinity in the limit of integration. So these are called improper. And they're evaluated using limits. If we're at an infinity, I can't just plug in infinity. I have to approach infinity. So that's where the limit concept comes into play. So there's going to be 3 different situations that we could be using. The first situation is where we're going from a number to infinity, which is what we were just looking at. We were going from 1 to basically a million, right, or a billion, or even bigger than that. We're going to rewrite that as the limit as b approaches infinity, and then we're actually going to integrate from a to b. So that's kind of the first situation that we may encounter, which is usually the most common, to be honest with you. The second situation, you may guess, is where you're going from negative infinity to b. So now we're going to set up the limit as a approaches negative infinity. And the variable is relatively arbitrary, right? It doesn't really matter what letter you use here, but we are very much used to going from A to B. So this should make sense to us, but we do have to set this up as a limit. And then we have a scenario that's a little bit harder to diagnose, but that's where we're going from negative infinity to infinity. Now, knowing that it's improper isn't the hard part, but actually setting it up, because now we have to have 2 limits. That's the part that gets tricky. You're going to have to take 2 separate integrals from negative infinity to some number in between. And it really doesn't matter what number you pick, to be honest with you. You could go negative infinity to 100 and then 100 to infinity, and that would cover all the space. But it's going to make a little bit more sense as we do some practice as to why we pick some of the numbers we pick. So once we break it up into 2, then we want to actually do 2 limits. So the limit as a approaches negative infinity from a to c of f of x dx, and then we're going to add the limit as b goes to infinity, and then we're going to integrate from c to b. That integral sign got a little funny, didn't it? Let's see if I can make that integral sign look a little bit better. Okay, from f of x, or of f of x dx. Remember, c is going to be your choice. So I'm going to go ahead and make a mark right there. C is going to be your choice as long as it covers all of the area, all of the x values in between. It's not really going to matter what you pick for c, but there's going to be some easier values along the way. So those are the 3 situations that we may encounter. Let's go ahead and do example 3 because I kind of know what the answer is going to be. We've already evaluated this using the Desmos and the calculator. We've taken a look at this. So let's look at how do we set this up with notation and actually do the calculus work without just plugging in some random points. Well, what we want to do is we want to diagnose it as improper, and we want to immediately set up a limit. So we're dealing with the limit as b approaches infinity from 1 to b of 1 over x dx. Now, you know how to get the antiderivative of this. So the rest of this is stuff that you know how to do. You just have to use your limit notation along the way. So we are evaluating ln of x from 1 to b. Now, I'm still taking the limit as b goes to infinity, so you cannot drop that notation. The limit as b goes to infinity of ln of x, ln of b minus ln of 1. That's our fundamental theorem of calculus. Plug in the b and plug in the 1. So now ln of 1 is just 0. So we are looking at the limit as b goes to infinity of ln of b. And I don't have to know a lot about this to know that as b gets bigger and bigger and bigger, the exponent is also going to get bigger and bigger and bigger. So that means that this is going to infinity. And because infinity is not a numeric value, that means that this integral diverges. I am not going to a specific number. My area is just going to continue to increase as I move along from 1 to infinity. My area just gets bigger and bigger and bigger. Now, just a slight warning because I have graded AP exams before. Right here, you cannot substitute infinity. What I mean by that is you cannot put equals ln of infinity right here. Okay, do not do that. Infinity is a concept. It is not something that you can substitute in for the variable. We can evaluate and get a result of infinity, but what we cannot do is just substitute in for a variable. So be careful with that. Let's go ahead. I anticipated this because I had evaluated it earlier. Now this one I anticipate will converge based on what we looked at in the calculator a second ago. So let's see what comes up with this. Well, how do I get this? Well, the first thing I'm going to do is I'm going to set up a limit because I see the infinity. So this is going to be the limit as b goes to infinity from 1 to b e to the negative x dx. Now there is going to be an extra negative here. There's a little bitty baby u sub happening. So there's an extra negative involved. So I've got the limit as b goes to infinity of negative e to the negative x evaluated from 1 to b. I still have to do the fundamental theorem, keeping my limit notation. I have not evaluated the limit yet. So we're going to say, I'm going to go ahead and move this down. I do not like negative exponents. Remember, they're very hard to work with. This is a perfect example as to why. So before I do the fundamental theorem, I went ahead and changed this just because I thought it'd be easier for you guys to look at. So this is going to be negative 1 over e to the b. And then it's going to be minus a negative, so that actually becomes a positive. And then 1 over e to the 1. Now, if I had not changed this, okay, if I had not moved this down and gotten rid of my negative exponent, I may just assume that this is infinity. But now that I'm looking at this, if b is growing, this whole term isn't getting bigger, it's actually getting smaller. This is going to 0. This is already just 1 over e. So knowing that, that is going to go to 0. The limit becomes just this value. So 1 over e is the exact value that this integral, this definite integral, is the area. This is the area under the curve for this definite integral, even though it's going to infinity. So earlier we got 0.36787. 7879444. Well, if you put 1 over e in your calculator, that's what you get. This is the exact answer. So this integral converges because we got an exact answer. We got a numerical answer for our definite integral.